Computer vision. So for a quick overview of what we're going to be covering the basis of computer vision and what it is, and then we're going to get into image processing, and then last, an introduction to convolutional neural networks, which are the backbone of computer vision, and then also maybe talk about some applications. So first off, what is computer vision? Computer vision is a field of machine learning that allows computers to see. And it's not seeing in the normal sense. In this sense, seeing is the computer's ability to recognize and process objects and images and sort of different items and images, etc. So there's many applications of this: object detection, image classification, segmentation, which is something you will find in the technical article if you read that, facial recognition, medical imaging, like being able to identify issues or problems in medical images and X-rays, etc. So we're going to be primarily focusing on the deep learning that's integrated with computer vision. There's many aspects of this field that lie outside deep learning and outside neural networks, but we're going to be focusing on that just for this course. And actually, this field of computer vision existed even before deep learning, so it's a lot more in-depth and complex than you would think, but we're just going to focus on the deep learning side. So the first thing we have to talk about is how can we take images and make them into something a computer can see? So what we do is we consider the image as a matrix of pixels. But the neural networks can't process a matrix, right? It only has one row of input vectors. So we have to flatten this image in order to give it to a neural network. So we take a matrix and we're going to make a vector. To show you an example of that, I'm going to show this example. So we have an image of a dog, and then we split that into different vectors and rows, and then we make it a long row. So we take each row and we stack it on top of each other. So for example, you might take like a 5x5 image and make it into a 25x1 vector. So I want to have everyone turn around and discuss with the people around you what feature you think I might have pulled out, like which specific part of the dog, like an eye, a nose, a whisker, or an ear. Like what did I take out and make into that one long thing over there? See if you can figure that out. Talk to the people next to you. I will give you the answer, but try and match that up. And notice that the blue lines between them are sort of the bottom of the image, so that can tell you where the image ends. An interesting question. Yes. If you have no idea, I'd like you to turn to your partner and tell them you have no idea. That's better than nothing. Could you turn to the person behind you and also include her in your discussion? Jeffrey, move one row forward and talk to your TAEs, TA group. I don't know what it's called. What is it called? What are the people in your TA group called? A TAE? Students? Fine, students. That's a boring term, but I'll take it. Students. Okay, I think I heard the answer in a couple of places, so I'll reveal it. It is in fact the ear of the dog, because I'm lazy and I took the leftmost thing that actually had things in it. So yeah, so basically that's sort of how computers are able to see images. They sort of take matrices of pixels like this and make it into one long vector. They might not do it exactly in this way, but this is a good way for you to visualize how they might do it. Okay, we also have to consider color values. In this matrix over here, I just put the pixels as colors, but that's not exactly how they work. In a matrix is going to be integer values, correct? So we need to consider how to do that. For a grayscale image, it's going to be very easy. Each pixel value is just going to represent how light or dark the pixel is. So it's going to look like that. So if anyone can see, you can see the slight shadow of the turtle in the image over there, because it's all numbers. It's not obviously the most clear thing ever, but it's more clear for a computer than the actual image would be. But with color images, you have more things you have to show. So here we're going to introduce something called depth. In depth basically talks about the number of matrices we need in order to represent an image. So these are called channels. Each matrix that we need to represent is called a channel. And each matrix is going to focus on just one color. So how many channels do you think we need to represent an image in color? Or what is the minimum number of colors we need to represent any color image? Printers? Oh, I heard it. Someone said it. Raise your hand and say it this time. 3. Yes, correct. So we're going to use RGB. We're going to have 3 different channels, a red channel, blue channel, and a green channel. And that's how we're going to represent our lovely little turtle over here. which means that for each thing, for each color image, we need 3 matrices, all that we input into the neural network at the same time. So you might be asking, why can't we use neural networks or like the existing neural network architecture? Why do we have to introduce this new field called computer vision? So again, a deep neural network will see these images as a matrix of values. And so the number of values is going to be the height of the image times the width of the image times the channels. For example, a normal 256 by 256 image will require in color, so like including the RGB, is going to require over 150 million neurons and weights. That is a lot of neurons and weights. Even for a neural network model that's really fast or really well optimized, that is a lot for it to handle. So because of that, it's going to have to analyze every pixel individually, so it's going to have more than 150 weights for almost every single layer. And because it's also analyzing those pixels individually, there's no spatial reasoning. It doesn't know if a pixel like is near another pixel, like what that means. Because when you come to images, right, you don't just look at one part of the image and decide something. You look at the things around it, the colors around it. You look at all the things that make up a feature. So there's no spatial reasoning or awareness in deep neural networks like they exist, like how we've learned them. And it's also vulnerable to shifting. If we have a whole sequence of weights and we shift the image a few things to the right, all of a sudden all the features are in different places than they're supposed to be, which means the DNN is going to be looking for a feature in a specific place, which is how the architecture works, and it's not going to be able to find it. So it's going to classify something completely differently just because it's shifted a few pixels over. So we have to make a completely new network for this to work. We need a model that has 3 things. First, it can reduce the number of weights necessary. If we have to have a weight for every single part of every single image, it's going to be way too many. We also need spatial awareness and relationships. It needs to be able to understand and look at pixels and the pixels around them. And lastly, it needs something called translational invariance, which is the ability of a model to recognize features no matter where they are in an image. So for a model with translational invariance, these 2 pictures, it would still be able to recognize all the features in them. Whereas a normal deep neural network that we've learned so far would not be able to tell that these are the same image because it'll be shifted to the right and it'll look like a completely new diagram to it. So let's get into convolutional neural networks. So these are a neural network that's specialized for image processing, and they have everything we're looking for. So the key components are convolutional layers, pooling layers, and fully connected or dense layers. We'll get into all of those later. So basically, how the neural network, how the CNN works, is it has fewer parameters because it shares parameters, which we'll learn about in a second. It has very high spatial awareness and has translational invariance. And it does this by using information locality, where basically it considers the image, like if you look at the 2 layers on the side, the first is a fully connected linear layer, whereas you can see every neuron is just connected to the output. Whereas in the locally connected layer, every neuron and the neurons around it are also connected to that same output, bringing in that sort of information locality aspect. So again, we're trying to take in the information around a node, and that's going to give us both the translational invariance and spatial awareness. So let's get into the powerhouse of a CNN. The powerhouse of the CNN are 2 things, convolutions and kernels. So a convolution is a mathematical calculation that is done to a section of an image to extract information about the features in that image. In this context, recall that a feature is like some sort of attribute of interest, such as an ear, like we went through before, number of legs, a certain color, etc. And so this is done using kernels. A kernel works like a sort of filter. It's a small weight of matrix used for convolutions, and it basically amplifies the effects of some pixels and minimizes the effects of others to try and draw out a specific feature or pattern. And this is done by matrix multiplying the section of the image with the kernel. As you can see in that image right over there, that's the section of the image we're taking. We're taking just that top right section. We're multiplying it by a specific kernel and getting an output. We're going to get into all of this math later, so don't worry if this image is not immediately understandable to you. So the result of each kernel calculation is going to be 1 square in the output matrix, which is also called a feature map. So you can see the result of that calculation, which is 8, is going to go into that last square over there, which is the feature map. Okay, so let's get into an example of a kernel. This is a very, very simplified idea of a kernel. So for example, this is a kernel that might be trying to extract the feature of an ear. If you give it the image of an ear, like that one is over here, like this image is supposed to be an ear, and apply the kernel, you're going to get a final value like this, 22. Again, completely fictionalized numbers and oversimplified, but let's get the idea of the math first. This value is going to be the value of the top corner of the output matrix, because I took this ear image from the top corner of the actual image. So then basically a value of 22 is really high, which means in that top corner of the matrix is going to be a high probability for there to be an ear there because this value is high. And so then this kernel is then going to shift across all the other sections of the image. And if it finds ears there, it'll also put high values. And if it doesn't, it'll put low values. So it's going to basically show, the feature map is going to show where in our model or where in our image there's ears or specific things like this that are present. So let's get into understanding more of kernels. So let's start to see how some of these kernels are going to be used in computer vision. So what do you think the output of the kernel on this input image is going to be? I'll give you a second to talk about it, but like you haven't worked with the kernels before, so like I'm not going to give you too much time because I probably won't get it. But does anyone have an idea? A guess? Doesn't even have to be an educated guess. I'll take any guess. So many blank faces. Okay, well, I will make you discuss for the next one. But for this one, is going to be vertical edge detection. So this kernel is going to look for the right vertical edges of an image. You see, basically it's looking for those edges over here, all the right edges of that turtle picture. So it's going to be trying to isolate those and sort of make those really obvious in the image. So everyone get a good clear image of this because the next one I'm going to demand student participation. Okay. Oh my God. What do we think this is going to be? So start thinking, like talking to the people around you about how this is similar and different than the previous one. So this is the previous matrix kernel, and this is the current one. So use that to get a better idea of maybe what this kernel is trying to bring out. If this one is virtual or vertical edge detection, what might this one be? Turn around, discuss with the people around you. Are you going to go around forcing people to interact? Emma and Tamsin or Jeffrey, and also going to make sure everyone's interacting. Look at the people around you, make sure they're interacting.
It was like horizontal edge connection because it kind of looks like the curves at the top and then at the bottom.
I'm hearing good ideas, good ideas. The ideas seem to have run out, but I'll give you guys a few more seconds. Okay, who has an idea for me? Someone better raise their hand or we're all going to sit here awkwardly. Yes.
Yeah, we thought it was like a horizontal edge detection.
Yes.
You can see like the curves at the top and the bottom.
That is totally right. Now, which edge do you think it'll be? Because like horizontal for vertical edge detection, we had right and left. So that one was specifically right. Which one do you think this would be? It doesn't have to be her. Someone else can, huh?
I was gonna say like, instead of left or right, it could be like top or bottom.
And then which one do you think it is?
The top?
So look at where the negatives are here and the negatives are here.
Oh, bottom.
Yes. Bottom edge detection. Perfect. So there's horizontal edge detection, and it's looking for the bottom horizontal images in this or edges in this image. Okay, now we're going to do a slightly more complicated one. This is a photo of our lovely education lead from last year. This is Bibav. And a kernel where everything but the middle is negative. What do you think the output is going to look like? What do you think this kernel is trying to do? Again, discuss with the people around you. And notice how in the previous edge detection kernels, all the columns or all the rows were different. But here, everything but the center is negative. It could almost be like, combine those. Okay, discuss with the people around you. What is your name right here in the front? Andrew? Andrew. And what is your name in the back right there? No, right you, white shirt. Huh? Kunchin? Kunchin, this is Andrew. Andrew? Oh my God, be friends, talk. If the conversation's ended, that means everyone is willing to raise their hand, right? If you're not willing to raise your hand, go back to talking. Okay, awesome. I'm going to see like so many hands now. Okay, what do we think this is trying to do? Where are my hands? People stop talking. Did I see a hand back there? Nope. Hand? Idea? Oh, yes?
Mm-hmm. So maybe it's trying to see like where the face is.
Uh-huh.
And then the idea, she said that it could be like detecting like where the laboratories are.
Mm-hmm.
Because in the middle is like dark.
Those are two very good ideas. The second one was kind of right. So what this is going to do is oh my god, total edge detection. So before we had one row or one column was negative. Now we have all of the outside is negative. So it's just trying to find those edges in the image. So basically, it's trying to like be able to isolate objects like that. Does everyone understand that kernel? Do we have any questions about kernels or convolutions so far? Totally understandable for yeah? It's going to change the intensity of the light. So basically, like instead of being black in the center, it'll be more gray. And then if you change the -1 to like a -10, the white's going to be more white. Any other questions? That was a good one, actually. Oh, yes? It's because the zero column. That zero here, this one has no zeros, and instead has -1 and 8. So it's going intense in the other direction. There's actually, where's the kernel? Okay, later in the slides, I will have basically the link to how Vibhav made these. There's a little kernel making thing you can do where you put in your image and then you mess around with the kernel and you can see all of these. So definitely check that out. You'll get a better understanding of how it works. That's how I figured out how this works. So, but yeah, it's that zero that's going to really mess it up. If you have the zero here instead, it'll be like less intense colors. Like it'll be more similar because it'll be 0 and -1. Yeah. I think they probably picked harsher shades here just so you could see the contrast a little bit more because like all of the edges are very, very small versus here they're like quite clear just because it's a line drawing versus like a real image of someone. Okay, let's move on to full convolutions. So we've seen how a kernel can transform an image, but how does the math actually work? Let's run through a quick calculation. So this is an example of a convolution. Let's assume this image over here or this matrix over here is our image, and that faint little thing over there is our kernel. So the first thing we're going to do is apply the kernel to the top left corner of our image, and then we're going to do a multiplication. So we're going to multiply all of the values by their corresponding kernel value. So in this case, I made it simple. I made everything in the kernel 0.1. So it's just all of the values of that top right corner times 0.1. And then we're going to do the summation. We're just going to do the multiplication and then add all those values together to get 1.5. And then 1.5 is going to be the top right output of our feature map. So then, again, we're going to do that again. Now we're going to move the kernel 1 over. And we're going to do the top left, or that was top left. This is top right. Sorry, guys, I don't know my left from my right. Top right. So here, now we're going to be looking, oh my God, I went ahead. Well, we're going to be looking at those, do the math again. And we're going to get that sum, and it's going to be 2.1 here. And then we're going to continue, sum, continue. And we're just going to fill those in until finally we get the entire feature map. And this basically, the intensity of each of those, or the weight of each of those things in the feature map is basically the intensity or whether or not a feature is present. So again, final output feature map. And here is where you can make your own kernels. I thought I put it earlier in the slide, but I didn't. Again, these slides are available for everyone in the weekly slides folder. So if you want to go try to use a kernel and mess around with it, I totally recommend you go here and do that. Okay, so now we learned all of this math of a convolution. And this is going to be basically what happens in every convolutional layer of a neural network. Each layer is going to take a predetermined kernel and apply it to the entire input matrix to get a new feature map and then send it to the next layer. And basically what this is going to be doing is revealing features and where they exist using a kernel. And because the kernel, like a kernel is applied to the entire input, we can find a feature anywhere it exists in the matrix, which is like in our translational invariance and also our spatial awareness. And because the kernel is reused, like those same weights are reused, like if you go back here, it's that same kernel that's reused for every single calculation. Because that is the case, we don't have to use as many parameters. We don't need an individual parameter for every single part of the input. We just have a smaller kernel that we apply. So our weights are going to be reused, which means we need less weights than we did previously. So again, that solves the three issues we were looking at: translational invariance, limited parameters, and spatial awareness. So now let's get into the hyperparameters of a kernel. So again, hyperparameter is basically the features of a matrix or a machine learning model that you can set and control. And so the actual weights of the kernel itself you can't control. Those are learned through forward-backward propagation, like most neural networks. But there are two things we can set about the kernel. Those are called stride and padding. So stride is basically the kernel step, or how many cells the kernel moves per iteration. And the padding is sort of an empty space added to the edges of images that allows, like, for example, the kernel to be applied in more places than it could previously. It allows like some features that might be in the very corner to be captured, etc. So let's get into a better understanding of stride. So basically, this is an example of a kernel with stride 1. Since it is stride 1, you can see that kernel only shifts over one row per iteration. So what do you think will happen if I have a stride of 2? How do you think this is going to affect how the kernel moves? And I'm specifically looking for how this might change the dimensions of the feature map. So again, as always, talk to the people around you. For those that just came in, find someone who was here earlier just so you have a better understanding of what's going on.
Oh, I'm not sure what you say for like your effect to anything on which, yeah.
By the way, a lot of the images I've pulled so far are from the technical article. So for those who are reading the technical article, you will see most of these images again. For example, the dog one, this one, the next one. A lot of images that I pulled from there. Yeah, I made these, by the way, just so you know. Okay, does anyone have an idea? Are you raising your hand? No, you were just scratching. Sorry, no, I called you out. So it's someone else raising their hand. If not, I'll go back to him. Who wants to save him? Somebody? Have an idea? Okay, what do you think is going to happen? Sorry to put you on the spot. Yes, that is precisely right. So because the stride is bigger, the kernel is going to move further away every iteration, which means it's going to reach the edge of the matrix earlier, which means there will be fewer iterations. And since the size of the feature map is directly proportional to the number of iterations, this means the dimensions of the feature map are going to be smaller. And again, all these images, technical article. Okay, so let's get into the other layers of a convolutional neural network. You will get into these in more detail in either the technical article or the literacy article, but we have first the pooling layer. So the pooling layer basically reduces the dimensions of the feature map. So that lowers the computational cost of future layers, so making it so that every convolutional layer doesn't get this giant matrix, it gets like a smaller one. It also reduces overfitting by generalizing more and sort of taking all those like small little changes and making them more averaged. It makes feature detection less vulnerable to noise and also positioning. So how it does that is basically you have two main pooling algorithms. You have max, where you just take a small section of the output matrix and then you take the max value of that, and that is the new value. Or you take the average. I'll show you that in the next slide. But then we also have dense or fully connected layers. These are present in almost every single neural network because these are used to make your final prediction. So in a dense layer, every neuron is connected to all the outputs of the previous layer, and it performs high-level reasoning after feature extraction, and it combines all of those features that all the convolutional layers pulled out and makes a final prediction. For example, for classification, it'll finally decide cat or dog, A or B, whatever it is. So for a more visual example of pooling layers, this is an example of max pool. So as you can see, in each region, it's just going to take that max value and then make it the new value of the new matrix. For average pooling, it's just going to take the average. So for example, that top one I think would be 4. I don't know, I can't do quick math in my head. But like it would be different values. Like for the bottom yellow one, it would be 2. For that one over there, it'd be also 2, I think, for the blue one. But yeah. Does anyone have any more questions so far about pooling layers? Any other stuff we covered? No questions? Am I just an amazing lecturer, or does everyone like have no idea what's going on? Well, we'll see when it comes for your homework. So that is what a total convolutional neural network is. You have the input, and then you put the input into a convolutional layer, typically multiple convolutional layers. For example, this one has like 6 or something, and then multiple pooling layers, and then maybe you do some pooling and then some convolution, like that. And then lastly, you have the dense and fully connected layers, which go into your output layer and actually does your final classification.